Greetings, this is Mr. T. In this video we're going to talk about Packet 4, Chapter 5 and 10, ionic and molecular compounds. I'll introduce ionic and molecular compounds, and then we'll spend the majority of Part 1 talking about ionic compounds exclusively, and then in Part 2 we'll get into molecular compounds. Now on the first page we have an outline showing the topic based on slides. However, as I go through the commentary, I'm actually going to focus on the key points and try to give you the big picture and practice the big picture. And then occasionally I'll make reference to the different slides. Let's first talk about ionic versus molecular compounds. This is where we combine individual elements that you've memorized from the periodic table to form compounds. And there's two types. There's ionic and there's molecular. So on the first slide, let's go ahead and introduce ionic and molecular compounds. In short, you know you're dealing with an ionic compound if you see a metal or a polyatomic ion and a non-metal. So for example, the best one to use is sodium chloride. Sodium, having memorized the metalloid barrier, so you know which side on the periodic table the metals are. Sodium's on the metal side, and then chloride is on the non-metal side based on the metalloid barrier. Then we know that this is going to be an ionic compound. Another example would be magnesium fluoride. Again, metal for magnesium, non-metal for fluorine, based on the location of the periodic table. So that's something that you want to memorize the pattern. The next one is going to be a molecular, or in other words, covalent compound. As you get deeper into chemistry, there's always two names for the same thing. So molecular and covalent are the same thing. So sometimes I'll say molecular compound, other times I'll say, or another professor will say, covalent compound. So these are going to be two nonmetals. So for example, I could have hydrogen, which is a nonmetal, and I could have chlorine, which is a nonmetal. So HCl is considered a molecular compound. Or I could have a fluorine and a chlorine, in which case this is also considered a molecular compound because they're both nonmetals. Now the tricky part, going back to ionic compounds, is polyatomic ions. So you could have one that looks something like this. NH4Cl, called ammonium chloride. Now this is considered a ionic compound because it's made up of the polyatomic ions that you had to memorize right at the beginning of this summer first week, first 2 days. So make sure to go ahead and have that memorized, and as soon as you see a single polyatomic ion, automatically it's going to be ionic. So even though technically everything in ammonium, NH4, is considered nonmetals because it's classified as an ion, a polyatomic ion, then it's ionic. So another example of that one might be hydronium chloride, H3OCl. And we'll get into the formulas and what that means. But for right now, I just wanted you to get into classification. The next core topic I want to get into is called the octet duet rule for ion formation. So on slide 10, let's go ahead and look at chlorine as an example to explain the octet rule and ion formation. So let's go ahead and draw the complete Bohr model for chlorine. Chlorine has an atomic number of 17. So let's go ahead and predict the Bohr model. There's the nucleus. So we have 17 electrons. We learned on the first energy level it can only hold 2. 1, 2. And then in the next one it can hold 8. 1, 2, 3, 4, 5, 6, 7, 8. So that gives us a total of 7 electrons left. So there's a third energy level that we have to populate. 1, 2, 3, 4, 5, 6, and 7. So this is the Bohr model. We learned that in the first energy level there's a maximum of 2 electrons that an atom can hold, and that's called the duet rule. We then learned that in the second energy level that ring can hold a maximum of 8 electrons. So that's called the octet rule. An octet rule. And nature loves 8 electrons in its rings. That's its goal in life. Just as we have a goal of becoming a millionaire, it wants a total of 8 electrons in its ring structure. So in the third energy level, and I'll just label the third energy level n equals 3, and I'll put an arrow there. You notice that there's about 7 electrons in the outermost energy level. So that's 7 valence electrons. Now, nature wants 8. Now, let's go ahead and figure this out. There's a total of, let's see, atomic number of 17. So there's 17 protons and 17 electrons. So it's got an overall charge of 0 because the charges balance out. But nature loves 8. So I'm going to go ahead and add in an extra electron. And that electron is going to go ahead and complete the octet. And nature doesn't mind this. So now you'll notice that the chlorine atom now has 18 electrons. So this is a good and bad thing. One, nature's happy because it's completed its octet in its outermost ring. The bad news is, however, that atom now has a charge. The chlorine now has a negative charge. And we discussed early on that anytime you have an atom with a charge, we call it a ion. So this is a the fancy name for this Cl minus, now that it's an ion, is called a chloride anion. And we'll get into that in a bit. But let me go ahead and prove to you that it has a negative charge. It started off with 17 protons, and now it has a total of 18 electrons. So it now has one leftover, has an excess of one leftover electron, so it has a negative charge. And usually we write the negative on the right hand side. It's not -1, that's like math, it's 1 minus. So 1 electron or a negative charge because of the electron. Now, so atoms love forming ions if it results in completing the octet or the duet rule. So let's do another one. Let's do hydrogen. it is possible for hydrogen to go ahead and form what's called a hydride, H minus. So it's got a single electron and it loves obeying the duet rule. So we'll pick up an electron. And now let's see, we started off with one proton, one electron, and then one proton, two electrons. So it went from 0 to a 1 minus charge. Now hydrogen will also lose the electron, forming an H+, and we'll get into that in a second. But let's go straight to this picture right here. This shows the chlorine again. Instead of drawing the entire Bohr model, I have the electron dot symbol. Notice it has 7 electrons, and nature loves completing the octet, so it picks up an extra electron, forming a complete octet and a negative charge. So this just shows us the number of protons and electrons afterwards, and then here is the electron arrangement showing the addition of the extra electron. And then on the next slide, slide 11, it shows you the math again, which I just went through right now. Now, this is a combination of a electron dot symbol along with the charge. Oftentimes we just get lazy. If we ever want to draw an ion symbol, then we just draw the atom or element with a charge like you see here. And the lone pairs, all these pairs of electrons are all implied. So let's talk about another scenario. And I'm going to go straight to sodium. That's not fluorine, that's sodium. Here's sodium. I'm going to draw the Bohr model again just so you can appreciate this one. There's 2. There's 8. And then there's 1. Now, nature loves having 8 electrons in its outermost shell, and it doesn't care how it does it. So there are some elements that instead of gaining an electron, what it will do is it will lose an electron. So using my black pen, there's my outermost electron. And what's going to happen is it's going to be lost. This results in exposing the octet underneath. So there's the octet underneath. Notice it has 8 electrons. Now it doesn't have to make sense. The magic number in chemistry land is 8. So as long as there's 8 electrons, then that particular element is happy. Now let's go through the charge on here. The sodium has a 1+ charge. Let's justify it. Original sodium has an atomic number of 11, so there's 11 protons, 11 electrons, and that's going to be 0. But when it loses an electron, 10 electrons, you're going to have an extra excess charge of 1 because of the extra proton. And so therefore it's a 1 positive. Now, 1s can be implied in chemistry as well. So just as the pairs of electrons. So again, just as the pairs of electrons are implied, that 1 can also be implied, which I just lost. And let me go ahead and rewrite that one. So just as the pairs of electrons can be implied, I've said that 3 times now, the 1 can be implied. So Na with a plus charge. Alright, so here is the starting neutral atom. There's the electron dot symbol. The unpaired electron is now missing. It exposes the octet underneath. But again, those exposed underneath electrons are implied, and the ones implied, so it just leaves a positive charge. And then here's the electron arrangement. We got rid of the electron, exposing the octet underneath. There's the difference in protons and electrons, leaving the excess positive charge. And here is another example showing the same thing, only this is a magnesium. Magnesium has 2 outer electrons. So to expose the octet underneath, it needs to get rid of both electrons. Consequently, there's going to be 10 electrons and 12 protons, so that's going to leave in excess of a 2 positive charge, which is proved on the next slide. So that's the theory about why atoms like to turn into electrons. Let's do one more. So let's do lithium. Lithium has 1 valence electron. Lithium has, if we just look at the nucleus, it has 2 electrons in its core and then 1 electron in its valence. So nature, if it can't do the octet rule, it does the duet. So it's going to go ahead and lose that electron. And when it does that, then it has 2 electrons in its outermost energy level. So we write lithium with a positive charge. Now it turns out hydrogen, even though I drew it as a hydride with 2 electrons, there's only 1 electron that, if there's only 1 electron, it actually likes to get rid of that electron and just have a free-floating proton. So technically that's not a duet rule. We don't know where to put hydrogen on the periodic table because it has so many properties. It's very complex. It can do all sorts of things. So it would be like an H plus for that. But the other ones, for representative elements, they are always duet and octet rule. Keyword is representative. So this pattern always works for representative. Transition metals, for example, are much more complicated, and their gaining and losing of electrons are much more complicated. So I've gone into detail explicitly about ionic versus molecular compounds, and then a lot of detail about ionic compounds obeying the octet rule. Notice how I didn't talk about molecular compounds and how they go from elements to molecular compounds. That's in a different chapter. So we're not going to worry about that for that one, for this video for part 1. Let's get into names really quick. We already talked about anions briefly. Let's talk about that one again. So if you have a sodium with a positive charge and you have a chloride with a negative charge, anything with negative charges, those are considered anions. So kind of underline the N. There's a little mnemonic trick. Whenever you see the N, that's negative charge. Any time you see a positive charge, we call these cations. So circle the T. The T kind of reminds me of a positive charge, so another mnemonic trick. Now, the proper name for this ion is going to be, for sodium, sodium cation. That's pretty easy. We took the name of the element and then just added the word cation afterward. Anything that's an anion is much more complicated. We have to have a suffix of IDE. So if the original name was chlorine, then we cut off the ene and we add in IDE, forming chloride. If I have a bromine, we cut off the INE and add in IDE for bromide. So that's a sodium cation, chloride anion, bromide anion. And I just said it again, bromide anion, pretty easy. Let's do one more. Fluorine would be a fluoride. F-L-U-O-R. Don't spell it O-U-R, that'd be wrong. It's not flour, it's fluor. So fluoride anion. Alright. Now we're going to go ahead and get into ion to ionic formula. So let's talk about ionic formulas. We're going to go from ions to ionic formulas. We're going to focus on a type of ionic formula called representative ions and then representative ionic formulas. And we'll get into variable and polyatomic ions after that. So here is an ion, sodium. Here is an ion, chloride. And then here is an ionic formula, sodium chloride. Now when they come together, the positive and negatives cancel each other out as long as they stick together. And then it creates a neutral species. So this is the whole reason why nature likes to form ionic compounds, because overall it's a neutral species, and substances that are neutral are considered stable. And nature gets the best of both worlds, where each species not only has obeys the octet rule, but they're also neutral. So let's investigate that a little bit further. So this is slide 16. We're going to be looking at ionic formulas. Let's go ahead and expand that. So total positive charges equal total negative charges. Therefore, we have a sodium positive, which is a 1 positive, and a chloride, which is a 1 negative charge, and it overall equals 0. And nature loves that, as I just mentioned. Here's another example of the same thing. So here's sodium. This is the electron dot formula. And then here's the chloride. Now, I made a big deal before how sodium would lose its electron, forming a sodium positive, and then fluoride or chloride would go ahead and gain an electron. What I didn't tell you was these two work in tandem, where when they're close to each other, neutral sodium and chloride do a chemical reaction. They actually shift electrons. It's not a true bond breaking or a bond making, but they do shift electrons. So that electron right there, when it gives off the sodium, is given directly to chloride, and that leaves a sodium that's positive and a chloride that's negative. Now the same thing happens with magnesium chloride, MgCl2. The magnesium donates its 2 electrons to 2 different chlorides. So let's reason this out. Here I have magnesium right there. Here I have a single chloride. Now the chloride is getting really messy, my apologies, but there's 7 valence electrons there, and I have 2 electrons that need to be donated in order for it to be a 2 positive charge, so that way it completes its inner octet. Unfortunately, we do not have enough chlorides, so I need to add in an extra 1. So that way 1 electron goes to 1 chloride, completing its octet, and then the other electron goes to the other chloride, completing its octet. So this diagram shows the same thing, albeit less messy. There's before, and then here is after. And that leads to magnesium chloride. So let's do another one. We'll do aluminum, and then we'll do fluoride. Now, aluminum needs to donate 3 electrons to achieve its inner octet, and then fluoride needs 1 electron each. So then we're going to need 3 of the fluorides. And 1 electron is donated to one fluoride, another electron is donated to the other one, and then the third one is donated to the third fluoride. That results in aluminum 3+, and that results in 3 of our fluorides. Now, I already mentioned that we do get lazy, and instead of writing 1 minus 1 minus 1 minus, we can just go ahead and write a minus. Also, for writing ion symbols, you do not have to put any pairs or unpaired of electrons around there. So in this case, we could do 3 fluorides. Now the next part. Ionic compounds can be written as names, or they can be written as ionic formulas. So we're going to be focusing on ionic formulas for right now. Ionic formula tells you the number of each of the ions. So in this case, there's going to be 1 of the aluminum and 3 of the fluorides. So the proper ionic formula is AlF3. Ones tend to be implied in chemistry, so the other way of writing it is AlF3, where the 1 is implied. So now you know where the subscripts come from. So going back to magnesium chloride, there's 1 of the magnesiums, there's 2 chlorides, and then we form MgCl2. Now, you know you have the proper number of ions if everything equals 0. So if I have 1 of the magnesium, which has a 2+ charge, and I have 2 of the chlorides, which is a 2- charge, the total number for positives is 2 positives. The total number of negatives is 2 negatives, and that equals 0. And that's how you know you're making the proper ionic formula. So now let's get into the tricks. These are little shortcuts to help you out. Although it's always nice to understand the theory to figure out how to make ions and ionic formulas, now we're going to be looking for the tricks or shortcut. So, taking out your periodic table, one of the reasons why we have the alternate 1A, 2A, and then 3A is so that way we can take advantage of the group properties. In this case, 1A, that has a hydrogen with 1 electron. When that comes off, it likes to form a 1+ ion. Again, 1 is implied. Lithium has a single valence electron. To form a duet, it needs to lose the electron and it forms a 1+. Again, the 1 is implied. So you'll notice a pattern. For group 1, all ions are always going to be +1. Group 2, they're always going to be +2, and then jump over to the other side, group 3 is +3. So one of the reasons why we have 1A, 2A, 3A is because these are the representative elements, and they go by the duet and octet rule reliably. So notice how we completely jumped over the transition element valley. Those play by different rules, and those tend to be where variable ions are. We'll get into those in a bit. Group 4 we're going to ignore. And then now we're going to go to group 5. So Let's go ahead and refresh ourselves with aluminum. So aluminum had, and I'm going to try to write the Bohr model. There were 2 electrons in the first energy level. There was 8 in the second energy level, and then there was 3 in the third energy level, and that's not 90 degrees, and sorry about that. But my point is this: it's much easier for aluminum to lose 3 in order to expose the octet than it is to gain 5. So aluminum will always be a plus 3. Now we cut out group 4 because it's a tie. Is it easier to gain 4 or lose 4? Well, both can occur. So we just pretty much ignore that. We're going to go straight to group 5, 6, and 7. In group 5, just looking at the Lewis symbol, you'll notice that it's closer to 8, so it's easier to gain 3 than it is to lose 5. So it likes to gain them. So this is going to be, all group 5 elements are always going to be -3, -2, -1. So my trick is to go ahead and at group 5 just do 5 minus 8. And that gives you the proper ion charge for groups 5A, 6A, and 7A. Now you don't have to worry about charges on the noble gases because they already have 8 valence electrons, so that doesn't count. Going back to the PowerPoint. So again, group 1, 2, and 3 is 1 positive, 2 positive, 3 positive, and then group 6, 8, 7, 8, 8A, doing the 6 minus 8, that gives you the 2 minus charge. So you can use this technique to easily figure out what the ions are in order to figure out the ionic formula. So let's move forward and show you another trick. So those are multiple examples forming ionic formulas, breaking it down by ions, but now we're going to use the other trick. Now, let's go back a step. If I had a 3 plus charge and I had oxygen with a 2 minus, in order for it to balance out, I would need to find the least common multiple. In this case, least common multiple is going to be 6. So I would need 2 of the aluminums and 3 of the oxygens in order to find Al2O3. But now I can use these tricks to immediately figure out what we're doing. Here's a trick. If the 2 charges add up to 0, then stick them together. On the other hand, such as aluminum oxide, if the 2 charges from each ion don't add up to 0, then you cross over. So there's that aluminum 3 plus, there's the oxygen we just did. They don't equal 0, they equal like -1, so then the 3 plus goes down here and it forms the 3. The 2 minus goes down here and it forms the 2. Now, some technical terms. Charges are always in the upper right hand corner, so we call those superscripts. And then the number of the ions is always down below, and that's the subscript. So let's go ahead and predict what the subscripts are for this one. This is magnesium with a 2 plus. This is sulfur with a 2 minus. You add them, they equal 0, so just stick them together, MgS. Let's do a phosphide with the 2 minus. Let's do a sodium with a plus. They do not add up to 0, so then you cross over. So that's Na3 plus. So the tricks always work for the representative ions. or representative elements that form representative ions. But things get a little bit trickier when we start getting into something called variable ions. So these are ones, it says memorize, but you don't really have to once you've learned the trick that I just taught you with the group 1, 2, 3, 5, 6, and 7. We talked about cations and anions, and we talked about the names of the anions and cations, so I'm just going to move forward. And then this is where we start getting into names for representative. Going back to our outline and our key points. We just finished going from ion to ionic formula, representative elements. And now we're going to go ahead and we're going to jump down to this line, name of ionic compounds for representative. So for example, here is the ionic formula for the ionic compound NaCl. The name is pretty straightforward. We learned that the name of the sodium with a positive charge is a sodium cation or sodium ion. And the name for the negative charged atom is a chloride. Notice how we changed the suffix, IDE. And we called it an anion. You probably get away with saying chloride ion as well, but the technical names is sodium cation, chloride anion. As far as the name of the ionic compound goes, all you got to do is take the name of the first element of the ion and a name of the second element of the ion and stick them together. So it's going to be sodium chloride. Now there should be a space in between. I always tell people to put like a 2-finger space or 1-finger space if you have big hands. And it should be a big space in between. So sodium chloride. Let's go back to the slides. So on slide 28, in summary, you take the name of the first cation, name of the second anion, and stick them together, sodium chloride, or potassium sulfide, magnesium oxide. Now the cool thing for the names of ionic compounds is you don't have to worry about the number of each ion. So for example, even though there is 2 potassium ions that make up that ionic formula, you do not have to put that in the final name. It's assumed that you could work backwards and reason out what the ions are and what the ionic formula is based on the names themselves. So another example, Al2O3, we ignore the subscripts for the number of ions and just write aluminum oxide. So we have examples for these. You can go through. Oops. So sodium bromide, sodium sulfide, Na2S, sodium nitride. So make sure to master these. You have to not only learn this process, but you have to be able to practice it over and over till you master it. You know you mastered it if you can do a time test on your own self-quiz and you're not stressed. Now we're going to get into variable ions and ionic formulas. Then we'll go ahead and get into the names of ionic compounds for variable. Variable ions tend to be found, not always, but tend to be found in the transition elements. And just as the name speaks for itself, elements are in transition. One of the properties that's in transition is the charge type. So for example, copper is a variable ion because it can choose to either have a 2 plus charge or it can have a plus charge. And usually we just summarize it like this: 2 plus or a plus charge. There is no way to figure this out on the periodic table. You have to coldly memorize it. So just as you had to memorize the polyatomic ions, you have to memorize the variable ions. There's two places you need to memorize. The first place is slide 32, and it shows you select variable ions. Notice the distinction between variable ions and single charge ions. So chromium can either be a 2 plus or 3 plus, as opposed to zinc, even though it's a transition element or transition metal, it only has a single charge always. However, these single charge ions, because they're found in the transition metal area, you have to memorize them. There's no way to look at the group number in transition metals to reason out what it is. So even these single charge ones you have to memorize. So one area is the slide, the next area is the syllabus. So on the very back pages of the syllabus, you've probably seen this before. This was a summary of the different polyatomic ions you had to memorize. And then if you screw up, you have the polyatomic ions you had to memorize. Well, now you have new stuff to memorize. And metalloids we already talked about, so you have to memorize those. That's pretty straightforward. We already have the halogens memorized. The alkali metals you already have memorized because they're in group 1, group 2. So what are the challenging ones? Well, over here, those are pretty straightforward. Those are all non-metal anions, so that's in a group 5, 6, and 7. Oh, that's not hard. Here's the hard part. You need to have all of these memorized right here that I am putting in green. The very top one, transition metals, they're single charge. That means there's only one type that it can ever be. It's not going to be one or the other. So silver will always be a +1. For the record, some of these actually have multiple charges. We're just trying to make it easier for you. And then these down here, these all have multiple charges, so we call these variable ions, because the ions vary. I should point out that there is one that I'm not going to test you on. Not going to test you on this one right here, because that one's just a little bit too tricky. That's a variable polyatomic ion. Even the name of it sounds tricky. So you'll just have to memorize the mercury with a 2 plus that you see there. All the other ones, you need to make sure that you've mastered those. Now you should already know the element names. Now you just have to memorize the charges. Some of the first ones are pretty easy. Iron's either a +2 or +3. But then as you go along, manganese, tungsten, wow, they've got a lot of potential charges. So you have to have all of those memorized. You'll notice that all of these variable ions are always going to be positive. So you don't have to worry about the negatives. And then gallium, aluminum, these are single charge. So let's go through some of the basics. As far as ion names, you use the same type of ion name like you did with the single charge ions. So just as Na+ is a sodium ion or a sodium cation, Cr2 plus is going to be a chromium cation. So what's the big difference? Because it can either be a 2 or a 3, you have to put the Roman numeral in parentheses. We call this a stock number. Now I've seen some examples where they hide the parentheses, but you always need the Roman numeral. So if you have a plus charge, which is a +1, then it'd be Roman numeral 1. If you were to have a 2 plus, then it'd be a Roman numeral 2. 3 plus would be a Roman numeral 3. So this is chromium 2 plus cation. And if this were a 3, as I try to modify it, then this would be a chromium 3 cation. Now the rest is pretty straightforward. If I'm trying to figure out the ionic formula, and I start off with a chromium 2 plus, and I have a chloride minus, then that's pretty straightforward. You can use one of two methods. You can use the charge balancing method. In this case, you can find the least common multiple. Least common multiple is going to be 2. So you just need one of the chromiums, and you need 2 of the chlorides. So there'd be a total of 2 positive, and a total of 2 negative, and that would equal 0, and then you'd have chromium chloride. Even easier, you can go ahead and use the cheat rule, and if it's like charge, or if the charges equal 0, then you stick them together. If they don't, then you cross over. Since they don't, you could always just cross over. So then it'd be CrCl2, or the 1 is implied on Cr. So ionic formula from the ions, that's pretty straightforward. Now, what becomes challenging is this right here. It's when you go from the this part isn't challenging. I'm just going to give another example of the same thing, and I think you guys will be okay on this. So here is gold 3 chloride. So automatically, because I have the Roman numeral 3, it's an Au3 plus. It's a chloride with a minus charge. The least common multiple in this case is going to be 3. So I'm going to need 1 of the gold, 3 of the chlorides, and then that gives me AuCl3. Or I could use the cheat rule where you'd have to cross them over. So that part's pretty easy. So let's do the hard part. The hard part is when you're starting off with the ionic formula and you're going to be going to the name. Now, I just taught you that the names have to include the stock number, but first things first. So let's start off with the easy part. So let's say I have iron chloride. First thing I'd have to do is go ahead and create my identify my individual ions. There's my iron, there's my chloride, so the name would be iron parentheses chloride, taken directly from the elements as ions. But now we need to go ahead and figure out what the charge is on iron. Is it Roman numeral 1 for a +1, Roman numeral 2 for a +2, Roman numeral 3 for a +3? So this is where it gets a little bit more challenging. And then here is my advice. You have to work backwards. Now, if it wasn't for variable ions, I could just teach you the cheat rule and you wouldn't have to do anything else and it'd be really easy. But I noticed how I taught you the charge balance rule, where you had to count the number of ions, and that's because we have to use that method and work backwards with that method. So for example, chloride is a representative, and because it's a representative, it's in group 7. So 8 minus 7 is -1, so this has a minus charge on there, or a 1 minus charge on there. We don't know what iron is. Iron can either be a +2 or a +3. It's going to be one of the two. Now, we know that we have 3 of our chlorides. Let's go ahead and count them. Total of 3 of our chlorides. So that's going to be a total of 3 negative. We know the overall charge on the formula is going to be 0. So therefore, we know we need a total of 3 positive for it to balance out the 3 negative for it to equal 0. Because we only have 1 iron, then here is our algebra problem. It's going to be 1 of whatever x is plus 3 equals 0. Excuse me. It's not going to be a +3, it's going to be -3. Let me explain. This is 3 negative. So then plus a 3 negative. Or that's the same thing as -3. So however you want to reason it out. But bottom line is if that's a 3 negative and then we have 1, that x has to be a 3 positive. So therefore, iron has to be a 3 positive. So going back to the original name of the ionic compound, and I'm just going to go ahead and put it in a black box. Because this is a 3 plus, this should be iron 3 chloride. So this is hard in my opinion, so let's practice it again. Let's do another one from this list of examples, and I'll just randomly choose one. I'll do PbO2. The name we can take from the ions. That's pretty straightforward. So that's going to be lead oxide. But now we need to put the stock number for the proper charge. We know it can either be a Pb2 plus or a Pb4 plus. It's going to be one of the two. So now we got to work backwards. We're just looking at individual ions. So in this case, one individual ion, it's going to have a 2 minus charge. We know this because it's representative. It's in group 6. So 6 minus 8, that's going to be a 2 minus charge. Now, we know that there's going to be 2, now that we figured out the charge on there, it's going to be 2 of the oxide anions. So we have to put a 2 here, and there's going to be a total of 4 negative, or a 4 minus charge. Now keep in mind that the positives and the negatives have to equal each other. So now we have to figure out lead. In lead, there's only going to be 1, and we don't know what it is. So we need 1, and then there's a total of 4 positives in order to balance out the 4 negatives. So it's going to be 1, and you solve for x, and x is going to be 4. So that means it's a 4 stock number, or Roman numeral number 4. Please keep in mind that you have to do this reverse charge balancing rules. That's the only way you can get the proper answer. A lot of people, they'll try to use the cheat rules in reverse, and that won't work. Because if you use the cheat rules in reverse, you would end up with a Pb2+, and that's the wrong cation. So you have to use this method in order to figure out what the stock number is. Not only do you have to know this, you have to master it. So go through these steps, and then given anything that has a variable ion that you have to pre-memorize, you should be able to immediately be able to go from the ionic formula to the name of the ionic compound. And if there is a variable ion, then you have to include the stock number for it to be considered correct. So this is challenging, and you really want to practice doing that reverse charge balancing in order to come up with the proper answer. So definitely know how to name those. If I'm getting a little too messy on slide 36, it shows you another example breaking down the ionic formula into ions, so you can do that reverse charge balancing to figure out what the stock number is. Slide 37 also has another example all worked out. So absolutely master those. And then more examples for you to practice with. So for example, the proper name for this one is going to be iron 3 sulfide. And then the proper name for this one is going to be copper 2 oxide. So we've talked about non-variable cations, or single charge cations, like representative elements, potassium, for example. We talked about variables. And now we're going to get into polyatomic ions. Going back to our outline. We talked about ion to ionic formula variable, name of ionic compound for variable ions, and now we're going to get into polyatomic ions. So part of this should be easier because you should already have these memorized. So going back to our syllabus, you should already have these memorized. So they are mastered. So perchlorate, chromate, phosphate, phosphite, sulfate, all these you should have mastered. Now these are examples of polyatomic ions. So ion means anything that has an atom with charge. And then poly means many. So you'll notice that there are, and I'll highlight this, there are many atoms that make up, I'll highlight it right now. There are many atoms that make up that specific ion. So NH4+. And there are many atoms that make up the positive charge ion. So that's a polyatomic. Compare that one to monoatomic. We're using my blue highlighter. There's only one atom that is used in making up that ion. And for variable ions, those are also considered monoatomic because, well, that's where it gets a little bit tricky depending on how you use the word monoatomic. So I'm not going to test you on the term monoatomic. I don't like that. So I'll just say single atom. So these are all single atom ions. And then copper is a single atom ion, although it's a single atom variable ion. Now your next question should be, well, is there such thing as a polyatomic variable ion where that 3 minus might become a 2 minus? No, never. Not for this class, ever. So you're only going to have single atom variable ions, which are listed here. And these are the only ones you ever have to master for all of chemistry. Furthermore, if you take chemistry at Valley College, these are the only ones you ever have to master for all of general chemistry. So if you got to take the next level, then you're already set. So let's jump right into this. So Windex, or any window cleaner, is made up of ammonium hydroxide. So you have a NH4 plus and an OH minus. So a mini atom charged molecule is a polyatomic ion. In this case, we have 2 polyatomic ions. Let's go from ionic formula to the name of the ionic compound. So you already learned that NH4 plus, that's going to be called ammonium. And because of the positive charge, we can call this ammonium cation. Although you could also get away with saying ammonium ion. And then OH minus is a hydroxide anion. Well, all you got to do is just stick the names together, and that's it. No extra changes are needed. So in this case, it's going to be a ammonium hydroxide. Again, no names, no name changes are needed. Even though hydroxide is an anion, the IDE is actually just naturally part of the name. So there's no name changes. So let me give you another example. So here is the ionic formula, NH4, and I'm going to use something like this. I'll use NH4 to SO4. Having already memorized these polyatomic ions, the proper name for this is going to be ammonium. Put a space in between. We're running out of space, so I'm just going to write it down right below it. SO4, having memorized it, is sulfate. I'm writing a little messy, obviously, but just to let you know, it's ATE. This is where spelling is so important, because if I were to sit there and say FITE, then I'm saying sulfite, and then this would be an SO3. More importantly, if I were to sit there and say IDE for sulfide, then I'm actually saying NH4 to S. Since a sulfide is a single atom charge from the representative groups. So spelling is everything. Let's do a couple other examples. I could have something like this. MgNO3 2. And so, having memorized the polyatomic ion name, it's going to be magnesium, and that's NO3, so it's a trait. It's not a nitride, it's not a nitrite, it's a nitrate. Let's get into another one, only this time I'm going to use a hydronium, H3O, and then I'll use, let's see, I'll use this one. So that would make this one an H3O 3P. So having memorized H3O, that's a hydronium, and then this is going to be a phosphide. phosphide. So careful, if I had put PO4, then that'd be a phosphate. So having memorized these polyatomic ions, then you should be okay. Now there's little patterns, but I would not rely on these patterns because there's a bunch of exceptions. So be careful on that. Also on the harder ones, such as HCO3, hydrogen carbonate, there is a space in between, or you could write the name bicarbonate. So for example, I could have something like this, NaHCO3, then it would be sodium, hydrogen, carbonate. Now the old school name that a lot of scientists insist that we have students learn is so bicarbonate. The bi is very confusing. It won't make any sense, so just have to memorize that if you see bicarbonate, it's the same thing as hydrogen carbonate. And so the alternate name is going to be sodium bicarbonate. So examples of polyatomic ions. Again, when it says memorize all polyatomic ions, you also have to memorize them from this syllabus. So please keep that in mind. So more examples of the same thing. Now, let's go ahead and do some more advanced ones, but before we do that, let's go ahead and explain how the formula works. So here I have a sodium, here I have a phosphide. Just going by charge balancing rules, the least common multiple in this case is going to be 3, because both 1 and 3 are multiples of 3. So therefore I would need 3 of the sodiums, and then the proper answer would be Na3P. Well, what we're going to do when we're figuring out ions to ionic formulas is we're going to ignore all of those extra atoms and just look at the charges. For example, I'm just going to keep that positive there, and I'm going to write NH4, NH4, NH4. Now all I'm going to do is just cover up, and I'll use a dark highlighter. I'm just going to cover up the atoms so all you see is the charge. And you know that you need 3 of those positive charges. So it doesn't matter what atoms make up that polyatomic portion, you just look at the charge. So you need 3 of those charges. So therefore, let me rewrite this again. Therefore, we would need 3 of the positive ions in order to balance out 1 of the negatives. And so it's going to be NH4 in parentheses 3 phosphide. Now you absolutely need the parentheses. Think of this as multiplication. So if I had something like this, two times 3, then that would equal 6. Alright? If I were to have 1 times 3, that would equal 3. So what this 3 is multiplying the entire polyatomic ions. So you need those parentheses around there. So the multiplication parentheses. Because that 3 means that we have 3 of those polyatomic ions that are needed. So let's do another one. If I were to have something like this right here, let's see. magnesium. And I'll just start off with an actual name, and I'll go to formula. So magnesium cyanide. And again, we didn't add the IDE, that's just part of the name for cyanide. That means there's going to be a magnesium with a 2 plus. There's going to be a cyanide with a minus charge. Again, we cover up the atoms, just look at the charges. The least common multiple is going to be 2. So I need 2 of the cyanides and only 1 of the magnesium for it to equal 0. So it's going to be MgCN, and you absolutely need that too. Now it's correct. Warning, if you write this on the, or type this, or choose the multiple choice answer for this one, it'd be completely wrong. Why? Because you're saying without the parentheses that there's only 2 nitrogen and 1 carbon. But with the parentheses, then there's 2 of the carbon and nitrogens, or there's 2 of the cyanides. So you need those parentheses. Now we're going to get into more challenging ones. We're going to combine polyatomic ions, and we're going to combine variable ions. So let me go ahead and I'll use iron. I'll use a different one. I'll say iron 2 oxide. And we're going to be going from name of ionic compound to the ionic formula. Oh, that's too easy because there's no polyatomic ion there. Duh. I know, we'll use carbonate. So this is going to be iron, and this is going to be a carbonate, CO3. Now, the 2 right there, that's pretty easy. It gives us a 2 plus. The carbonate, that gives us a 2 minus. And we only need 1 of each, so the least common multiple in this case is going to be 2, and you only need 1 of each, so it's just going to be FeCO3. That's pretty easy. Now let's do the opposite one. Now we're going to go from ionic formula to name of ionic compound. Much more challenging, and we're going to use variable ions. So let's see. Let me go ahead and do one. Let's do PbOH2. First off, just by the polyatomic ion and the ions, you should already have the written portion of the name down pretty easy. So that's going to be lead hydroxide. Now the hard part, we have 2 hydroxides, each with a negative charge. So we're going to have to use reverse charge balancing rules. So we got a total of 2 negative. For it to equal 0, we need a total of 2 positive. There's only going to be 1 of the lead. And so this one would have to be a 2 positive since there's only 1 of them. So that balances out the 2 negative for it to equal 0. So this would have to be lead 2 hydroxide. So there's a ton of formulas to names as examples that you can practice with and go through each of these. And you can see all the different uses for them, from calcium replenisher, calcium phosphate, to antacids, which everybody's probably starting to get into now. I know I would if I were a student. I've been there. Magnesium sulfate, Epsom salts, so a lot of good stuff. I love this example right here. because you really have to make sure you know your representative elements, transition elements, and for the single atom charges, they're going to be ides. For the polyatomic ions, you have to have memorized. So for A, the answer is going to be it's going to be 3, 1, 2. And then for B, the answer is just shown for you right now. So be sure to practice those. More examples for you to practice with. And then more examples for you to practice with. So you notice these are variable ions and polyatomic ions. So my recommendation is to rewind it a bit, see if you can come up with the answers, and then compare the answers to compare your answers to the answers in the commentary answer key. And this concludes our part 1 of ionic molecular compounds. And let me finish the last one off so you can take a look at it and practice it. Good stuff.